Or can I just talk as much as I want because it's the last talk? Elena is really scared. Okay, so I'll try to be concise. So it's my job is now to talk about the famous cusp. We've heard cusp. I think there hasn't been a single talk that did not mention the word cusp. I'm supposed to talk about the observation. Okay, yeah, you did. So I'm supposed to now talk a bit about the observations, what we know about observationally. It's been following me. It's kind of a Moby Dick thing, trying to hunt the cusp, and sometimes it's there, sometimes it isn't. People get angry at me or not, and so I'll try to tell you why it's so complex. I think Tuan has already done a very good job when he showed, and here's a 4 parsec half-light radius nuclear cluster, and you basically don't see anything in the lower half. And at the same time, I hope not to confuse you too much, and so the cusp is there, I would say. What we see is consistent with there being a cusp. So quickly, at the galactic center, you have a supermassive black hole, in case you don't know that yet. You may have missed that. And of course, there's a cluster around it, so that's, I say 25 million solar masses, whatever. So that is, okay, it's not working. So we have heard about that before, and I don't want to get into there, but because I still have a very faint or weak intellectual grip on stellar dynamics, but let's just say cusp formation has been predicted by many people with a lot of different methods, and it's an extremely robust result of stellar dynamics. I mean, I think nobody has tried to simulate a cluster on a black hole and did not find a cusp. Nevertheless, it's a problem that is difficult to study observationally, basically because extragalactic systems are very far away. The galactic center is a unique test case. There we can actually count the stars and resolve, and it has a lot of implications for physics. So it's not just a purely academic exercise to see whether we've got the mathematics right, but there's lots of physics in there also, role of stellar collisions, tidal disruptions, MRIs, etc. So if you have a simple case, so this is actually old work. This is Todd Lauer, I think it's 1998. This is M32, satellite galaxy of the Andromeda galaxy. It has a central black hole of a few million solar masses. There's no nuclear star cluster. It's an old thing. There's no dust in there, no very recent star formation. So that's actually relatively simple. And basically where's the laser? So basically this is light profile, and it's pretty much consistent with a classical cusp. Now, in the case of the Milky Way, you're much closer. You have a black hole of about the same size, but a much larger galaxy around. But you see already it's kind of messy. So you have a Bartlett type galaxy. You have lots of dust and gas. You have repeated star formation, not continuous, but repeated star formation. So it's a mess. And also you have lots of different stellar components superposed. You have a bar, you have a disk, you have a bar, you have a nuclear disk, you have a nuclear star cluster, and the whole thing projected in 2D, and it's really complicated. So this is from our survey that we're carrying out with my group now, a nice color image just to wake you up. I'm here to entertain you in the last minutes. So let's go to the measurements directly. So this is what has been found. This is kind of the state of the art a few years ago. Projected radius in parsecs from the black hole, so out to 1 parsec, 2 parsec, number density, and this is just the late type stars, so the giants, the supposedly old stars. Not all of them are old enough, because when I say cusp here, I want to be clear, I say cusp by 2-body relaxation, an old thing. So you need stuff that had the chance to relax. So we're talking about order Hubble times, or if you're a bit more optimistic, if you throw in other effects like massive perturbers, mass segregation, etc., you can maybe go down to 1/4 of the Hubble time, but let's say a few billion years you need them to build it. So you see, okay, nicely here your stellar density is rising, and then something happens at 0.3, 0.2 parsecs, and then it's flattish. Tuan has showed that. And that is the missing cusp problem. And it's not missing here. Let me point that out. I mean, they always say missing cusp. Well, out here everything is fine. It's just a simple 0.1, 0.2 arc seconds. And that has led to a flurry of activity, huge theoretical activity. And of course, it's highly relevant. Do we have our things right, our theory? What about the physics? I mean, what do we know? Is there a hole? Is there a core? What is happening? What is the density of stars? Can we exclude extreme mass ratio in spirals if there's no cusp? Also, this can tell us about the formation history of the nuclear star cluster. Maybe it's not relaxed after all. So, so there's a deficit of giants around ZJ star. Okay, forget about this brightness thing. I would really say there's a deficit of giants. Basically all brightnesses. It's a bit brightness dependent. I don't show that plot. We're still analyzing that. So the brighter, the more deficit, I would say. But so that then people try to explain this. So you have, of course, two grosso modo, two different possible interpretations. So no, it's not gross. It's it's maybe gross. There's no cusp. So either what you see is really representative for what's there. So the cusp is not there, or of course, what you see is not representative for the entire nucleus cluster. And then, of course, you have different submodels. So, for example, it's not yet formed, long relaxation times, what David Merritt suggested, or maybe it was destroyed by some infall, but we know there was no major merger in the Milky Way. So that's highly improbable also. Or then, of course, there's this other branch that says basically you have to alter something about the giants, which basically means to have to make them invisible, which means you destroy their envelopes by different mechanisms, star-star collision and so, which is not very effective. Then one of the things that could work is what Pau suggested, that, I mean, there's young stars where we don't see the cusp, there's young stars. The young stars formed in a dense gas disk. The dense gas disk, there must have been clumps of protogas, and of course that enhances your cross-section. You punch through that and you remove a bit the giants. So that's actually one of the, it actually explains also why you miss giants where you observe young stars. So I like that very much. It was Chen and Amaro Suyane. But I don't go into this interpretation. I'm an observer. I'm an empiricist. So I just ask the question, how good are our data? A lot of that work has been presented by myself, so I knew how crappy the work was, and I said, okay, let's go back and work again on that and try to make it better. I mean, never crappy. You always do the best that you can, but a few years later you repeat your experiments and see, okay, I can do this better. So we have to deal with this extreme and highly variable extinction. Then, of course, the problem that the nuclear star cluster is not isolated, which is something that is never being mentioned because all the theory papers deal with a black hole and a cluster around it, and that's floating in vacuum. But this thing is not floating in a vacuum. It's floating in the galactic center. So there's other stuff overlaid on it. The light density, for example, we can't use that in the galactic center. It's completely misleading. We can use it, and I will do that, but that takes a lot of work. And of course, we have the complex stellar population. We see only the tip of the iceberg. So what we tried was digging deeper, and it's taking us 3 years of work, I think, and another year of referee work. So we did deeper star counts. We took some very, very good data. We stacked them, so we added them to get higher signal to noise. You can do that because, I mean, the motion of the stars is much smaller than the diffraction limit. So you can easily take 2 or 3 years of data and stack them in the worst case. Set S2 maybe is a problem, but we don't care in that case. And the other thing was, and that was really something entirely new, I got good enough over the years to remove the stars. So all the bright stars, and take a look at the diffuse light that's left, and that's there from the unresolved stellar population. So first, this is the luminosity function. So this is the brightness, magnitudes, and that is the number of stars that we see. So this is what we see. Here's the limit of spectroscopy, roughly, give or take a magnitude, depends how much time you spend. So this is where you can know what kind of star you're looking at. And here you just basically have the brightness of the star to give you a rough idea what it is. We can't measure the colors, again, because we're limited to the infrared. So we don't really know what we're looking at the galactic center. This is the old completeness limit. Of course, we also, depending on where we are in the field, we have a given probability of detecting a given star. So the whole game, I mean, counting stars sounds like the simplest thing you can do. And it's definitely very complicated in this environment. So this is the old state of the art from Schödel et al. 2007, and we got a magnitude deeper. We were very happy about that, because we thought from models of continuous star formation that there we would get only old stars. During the referee process, we found out that it's not that way. We are completely dominated by these stars here. There's this red clump, that's the helium core burning stars. This kind of the main sequence of the giants, as you could say, and they dominate all existing star counts so far, everything that was published so far before us. The other thing is the diffuse light. So here, I've taken a narrowband image here because it's much clearer. This is a bracket gamma emission line map. After I remove all the stars, I see the so-called mini spiral. I see this thing here. This is the bright guide star. This star is just so bright that it creates you this crosshairs from telescope diffraction from the spiders that hold the secondary. But you see the gas. And if you compare that with the Paschen alpha emission map from the HST, from some work that a postdoc, Hui Dong, has done, but you can then use the HST gas map and scale it and remove the gas. You have to do that. You have to get rid of that. Because if not, you measure something that has nothing to do with stars, because the gas, the diffuse light from the gas is stronger than the diffuse light from the gas. We have done a lot of simulations, and it works. So one of the referees said, yeah, but is that really true? And we did really all kinds of simulation. It really works. Okay, now this is the important plot of the talk. Now you can wake up. Again, we have the distance from the black hole here. We have the stellar density. This is a mix. So I throw light density measurement from the diffuse light and also star counts into the same plot. And we had to do some other dirty business. We had to take at larger distances, about 2-3 parsecs, we had to take some other data and scale them. Because the problem is we want to deproject the whole thing, and you can only deproject if you have the light distribution or stellar distribution out to very long distances. And we did something else. Sorry. So this is so the black stuff is the diffuse light. This is really unresolved stars. They're roughly solar mass. These are the subgiants or main sequence stars. These are the faintest stars we can count. So this is just a line drawn there. This is a power law. And there's a power law through the red clump stars, or you can also take all giant stars. And you actually see, again, the giant stars, it's not such a big problem. Everything basically looks the same. All stars look the same, except that you have here this dip, and of course in the innermost part, the giant stars really fail you. But it's not a huge problem. At scales of a whole order of magnitude, everything looks fine. And of course here you have this, and then you drop off. So what we've done here, you see that really goes basically down to 0 here. That's because we have subtracted, we have used some dark clouds and really scaled in a way that we make sure we don't have any fore or background emission in there, which contributes, of course, systematics. We took that into account in error. And so in the end, what we get is we fit a 3D Nuka law. Nuka law is usually used in 2 dimensions. You can use it in 3 dimensions. It's basically a generalized broken power law. And so you get for the 3-dimensional gamma, so just the power law density, something like 1 point something-ish, 1.1 to 1.3. Basically, that works for all the stellar populations that we see. A break radius of around 3 parsecs, which is so basically out here where you then have the steeper decrease. That's roughly the radius of influence of the black hole. And finally, we also did some simulations. So we say, OK, we have a cusp. That's a cusp profile. It's not a core. The problem is it's so much flatter than the Barkholt-Wolff cusp. Well, so then Holger Baumgart and Pau Amaro Seoane, and OK, the Schödel guy is here because he provided the data, but it's not because he's a great N-body. I'm an N-body ignorant. So here you see again the star counts, the faint light density, and then red is the simulated cluster. And the trick is basically, if you look at this color magnitude diagram of simulated, we had several star formation events in there. We just did not have just a 10 billion year old cluster that then evolves passively. Then you get a Barkholt-Wolff cusp, of course. But we know you have 80% of the stars. So this, again, Oliver is being mentioned. He doesn't have a talk, but we should mention him a lot. Oliver Poole, star formation history. So some of the stars are young. Then they probably did not have time to fully relax. And of course, what you then end up is with a cusp that is much shallower than the classic Barkholt-Wolff cusp. Because, OK, that depends a bit how you throw the stars into your system, but basically it's consistent. Of course, it's consistent. OK, we don't have to talk about that. So I'm going to finish soon. So just a few minor annotations. So here I say, basically, I tell you what we see is consistent with having a cusp. It's definitely inconsistent with having a core. And so still some minor question that's more for the galactic center specialists now. So again, you have this again. This is a famous, nice thing from Tal Alexander. This sketch that we use a lot to explain the galactic center. So you have a black hole, you have the red stars. That's the old cluster. Then you have the disk of the blue stars, and you have lots of young stars. And so now you could say, okay, but what about this recent star formation? Did it mess you up? I mean, what's the contamination? So here's a fun thing that we did. This is the green line here is our measured luminosity function at a distance of 2 arcseconds from the black hole. And now if you take from the published work that was done at the MPE and then was done at UCLA, we take the properties of this disk of young stars and basically how it's radially distributed, you normalize it, and if you just take a standard, for example, Krupa initial mass function, then you see that's the black line, that at faint magnitude suddenly we would see so many stars, much more than we see actually in total, or we would be dominated by we should be seeing far more stars than we actually see. However, if I take a top-heavy mass function, that means we form much more massive stars than faint stars. This is the red or green or blue lines. Then actually we have much less young stars at this distance than what we actually measure. So that's just as a corollary, just from the luminosity function analysis, we know there must be a top-heavy mass function. That has been, by many people, have found a top-heavy mass function with different ways, and that's yet another way of showing that the most recent star formation event 3 to 6 million years ago must have been severely top-heavy. And finally, a caveat from the star count. So I used the star formation history from the central parsec as determined by Oliver Pfuhl. And this is nothing that that was pointed out by Tobias Fritz. That was not pointed out by the referee, but some other colleague said, but careful, look at the star formation history. What is the ages of the stars that you look at? And so basically I took this star formation history and calculated the fraction of stars that are older than 3 billion years, roughly saying, okay, if I'm optimistic, if something is older than 3 billion years, it should have undergone maybe some kind of relaxation. And then you see that this is the bright giants that we see. Not all bright giants are old. That's important. Not all bright giants are very old, but most of them. And then where we thought that the 18th magnitude stars, these are the faintest stars that we can really detect and count. And when we initially started our work, we thought these are ideal tracers. And when we had it finished and the referee process, depressingly, we find out they may be the worst possible tracers. That depends on what you know. If you just take the known star formation history, there's a lot of uncertainty, systematic uncertainty, but it's a big caveat. They may be bad. But again, in my conclusions, I have to say that we find this shallow cusp at all stellar magnitudes, except in the central 0.2 or maybe 0.3 parsecs for the giants. So wherever we look, we see a cusp-like profile. So it would be very surprising if there is no cusp. In particular, the diffuse light, the faint diffuse light, is solar mass stars. So that stuff is definitely old. So the missing cusp, we also have an agreement between theoretical predictions, between our modeling and our data. That's the first time we can have agreement between what we see and what we model. Okay, if you're a cynic, you say, okay, yeah, you see something and you model, make your model to fit what you see. Okay, but it's a very, very simple n-body model, so there's nothing was fine-tuned there. So the missing cusp problem is really, in my opinion, the state of the art, to the best I can tell you. I mean, I may have done some horrible mistakes, but to the best we can tell, it's limited to the central 0.2 parsecs, I would say, and roughly 100 stars are missing. This is not a huge number. There are various explanations. I really favor what Xian Chen and Pao have done. And then some other things. So we predict 370 stars per square arc second at 19.5 to 20.5 magnitudes. I'm not sure whether that's good or bad, for whether that agrees more or less with what you use for gravity. Density is a few times 10 to the 7 stars per cubic parsec, 0.01 parsec. That's the density of the stars that we see. That's the density of not black holes. It's just the stars that we see, which is like 200 solar masses inside the S2 orbit. And the good news is that can be resolved with a 30 or 40 meter class telescope. So in hopefully 10 years, we can see it. And then we have some corollaries that we have this top-heavy IMF of the recent star formation. These are the papers. So a student of mine, Lali Gallego, she has done very hard work on the star counts. Then there's this diffuse light paper, and then Olga Baumgart. And I hope you're not too tired now. Thank you.